Welcome to the Deep Dive. Today we're plunging into something pretty exciting at the edge of AI research. We're talking about unlocking true reasoning in machines, really moving beyond what even today's best large language models, the LLMs, can manage.
Exactly. We're looking at a pretty radical new AI architecture. It's called the Hierarchical Reasoning Model, or HRM. And what's really fascinating, I think, is that it's directly inspired by how the human brain seems to work.
Right, and this deep dive is based on a specific research paper, Hierarchical Reasoning Model. The authors are Guan, Jin Li, and their colleagues over at Sapient Intelligence and Tsinghua University. So our mission today is basically to unpack this. We want to pull out the core ideas, understand how HRM actually functions, and importantly, figure out why it might be such a game changer for AI thinking and problem solving. We'll get into why it's so efficient, so powerful, apparently even outperforming massive LLMs on certain kinds of tasks. So yeah, let's get into it.
Okay, so the big challenge, really the central challenge in AI right now, is reasoning. Getting machines to actually figure out and then execute complex sequences of actions to reach a goal. Despite all the progress, you see amazing things, but this reasoning part, it's still a major hurdle for getting to true AI.
And the current big players, these LLMs, they mostly use this technique called chain of thought, right? CoT, I think most of us have seen that, where it kind of spells out its thinking step by step.
You've got it. CoT basically externalizes the reasoning process. It lays out every single step as a token, like it's narrating its thought process out loud. But, and this is crucial to the paper's argument, they call CoT a crutch, not a real solution.
A crutch? That's a strong word. Why do they see it that way? What's wrong with spelling things out?
Well, think about a really long chain of steps. If just one link, one step, is wrong or slightly off, the whole thing can just fall apart. It's brittle is the word they use. And beyond that, it needs tons of training data for the model to learn these step-by-step decompositions. Plus, generating all those intermediate thought tokens, it's slow, it's computationally expensive.
Okay, so it's inefficient, it's brittle, but it sounds like there might be a deeper issue, a fundamental limitation with the LLMs themselves.
Precisely. That's what the paper argues. Despite how impressive they are, LLMs have what they call a shallow core architecture. They're not Turing complete. Now that sounds technical, but it points to a fundamental ceiling on their intelligence. It means LLMs can't inherently solve problems that require deliberate algorithmic reasoning, the kind of thinking that involves complex planning, symbolic manipulation, the stuff we associate with real problem solving. The paper even mentions, look, just making a transformer model deeper, adding more layers, it doesn't really help with hard problems like, say, Sudoku. There seems to be an architectural block.
That's a really key distinction. So they're amazing patterns matchers, but maybe not true algorithmic thinkers. So if that's the limitation, what's this idea of latent reasoning that HRM is aiming for? Why is that different?
Yeah, latent reasoning, contrast with how we think. Our brains can sustain these long, complex lines of thought, coherent reasoning incredibly efficiently, and we do it internally in this latent space, this hidden state, without having to constantly translate everything back into words or language. Current AI models, they really struggle with that. You run into problems like vanishing gradients.
Ah, right, where the learning signal gets weaker and weaker the deeper you go.
Exactly. It basically makes really depth computation ineffective. And you might think, okay, what about recurrent architectures? RNNs, they seem like a natural fit for sequences.
But they have their own issues too, don't they?
They do. They often suffer from what's called early convergence. The computation just kind of stalls out too soon, limiting how deep they can effectively reason. And they rely on this technique called backpropagation through time, BPTT. BPTT essentially means the model has to remember every single step it took during learning. It has to store all the hidden states. This leads to what's called an O-A-T memory footprint. Basically, the memory needed grows linearly with the length of the task. For long tasks, it becomes completely impractical. Plus, it's generally considered biologically implausible. Our brains probably don't work that way. So yeah, current methods are limited, and the traditional alternatives have these major drawbacks.
Okay, so faced with these limitations, these architectural walls, where do you look for a better way? The paper argues pretty convincingly that the human brain itself offers a blueprint, a model for achieving that effective computational depth that AI currently lacks.
Yes, and HRM tries to directly mimic some key principles from neuroscience. First, there's hierarchical processing. Our brain isn't just one big mush. It organizes computation in hierarchies across different cortical regions. You have higher level areas dealing with abstract stuff, longer timescales, planning, and lower-level areas handling the fast, detailed, immediate processing.
And it's not just different levels, it's also about time, right? Temporal separation.
Exactly. These different hierarchical levels in the brain operate on distinct timescales. You might have heard of brain waves, like slow theta waves and faster gamma waves. This separation is key. It allows the slower, high-level processes to provide stable guidance for the rapid, low-level computations without getting overwhelmed by the details, like a general planning the strategy while the troops execute tactics quickly.
Makes sense. And the third principle?
Recurrent connectivity. The brain is full of feedback loops, connections going backwards and forwards. These loops allow the system to iteratively refine its internal representations, its understanding. So the slow, higher levels guide and the fast, lower levels execute. But there's this constant feedback maintaining coherence. And crucially, the brain seems to do this without the huge computational cost, the credit assignment problem, that plagues standard BPTT and artificial networks.
Okay, so drawing inspiration from these brain principles, hierarchy, different timescales, recurrence, the researchers built the Hierarchical Reasoning Model, HRM. It's designed specifically as a novel recurrent architecture to, well, dramatically increase this effective computational depth.
That's the goal. And at its heart, HRM has these two interdependent modules. You can almost think of them as like two specialized brains working together. There's a high-level module, the H module. It handles the slow, abstract planning, the deliberate reasoning, and importantly, it only updates after the low-level module finishes its part of the job.
And that low-level module, the L module.
That's the workhorse. It handles the rapid, detailed computations. It executes the subordinate processing needed for the task at hand. It can actually run through multiple computational steps within just one cycle of the high-level module. So yeah, the H module sets the strategy, the L module does the fast, detailed execution, and they work together to keep the whole process coherent.
So how does this two-part system actually achieve its power? They talk about some innovative mechanisms, starting with hierarchical convergence. How does that work? You mentioned standard RNNs stall out early.
Right. Premature convergence is a big problem. HRM tackles this cleverly. The L module, which is kind of like a standard RNN in some ways, does converge within each cycle. It finds a local equilibrium, a temporary stable state for its computation. But here's the trick. The H module then provides a new context, a new set of instructions or guidance. This essentially restarts the L module's computation for a fresh phase. So instead of stalling, HRM can perform a whole sequence of these distinct, stable, nested computations. This allows it to achieve a much greater effective computational depth. They quantify it as n times t steps, where n is the number of high-level cycles and t is steps within the low-level cycle.
That's neat. It avoids the stalling by periodically resetting the stage, so to speak. What about training? You mentioned BPTT was a memory hog.
Huge memory hog. OT, memory. HRM uses something called an approximate gradient for training. It's a way to estimate the gradient needed for learning without doing full BPTT. The key outcome is that it only requires O1 memory, constant memory, regardless of how long the task sequence is.
So the memory needs don't grow with the task length at all.
Exactly. It stays flat. Think of it this way. The model only needs to remember information about the very recent local computations, kind of like local synaptic activity in the brain. It doesn't need to unroll and store its entire computational history. This makes training vastly more efficient and, again, feels more biologically plausible.
Okay, efficient training. They also use something called deep supervision. What's that about? Inspired by brain oscillations.
Yeah, the idea is inspired by how periodic activity in the brain might help regulate learning. In HRM, it works like this. The model runs forward for a certain number of steps, a segment. After each segment, they calculate a loss, update the model's parameters, and then, this is important, they detach the hidden state from the computational graph. Detaching means the gradients don't flow back beyond that segment. It provides frequent learning signals, especially to the high-level module, acts as a form of regularization to prevent overfitting, and improves overall training stability. It's like giving the model frequent check-ins.
Got it. Frequent feedback, stable learning. And then there's adaptive computational time, ACT. You mentioned thinking fast and slow. How does that work in the model?
This is really cool. It's inspired by Daniel Kahneman's System 1 and System 2, thinking the idea that our brain switches between fast, automatic processing and slower, more deliberate, effortful thought. HRM uses a Q-learning algorithm, which is a type of reinforcement learning. Basically, the model learns to decide at certain points whether to halt its computation for that step or continue processing for more steps. It learns to dynamically allocate more computational effort when the task seems harder or requires deeper reasoning.
So it can decide to think harder on the fly?
Pretty much. And the payoff is significant computational savings. The paper shows ACT can drastically cut down the number of steps needed with only a minimal hit to performance, sometimes none at all. It learns to be efficient with its thinking time.
And one last mechanism, inference time scaling. This sounds useful.
It really is. It means after HRM is trained, you can actually boost its performance on difficult problems simply by allowing it to run for more computational steps at inference time when it's actually solving a problem, not learning. You just increase its computation limit, Mmax, without any retraining or changing the model itself. This is particularly effective for tasks like Sudoku that really benefit from deeper reasoning.
Okay, so you've got this brain-inspired architecture, hierarchical convergence, efficient training, deep supervision, adaptive computation, quite a toolkit. What does it all add up to in terms of performance? You said it's efficient.
It's remarkably efficient. We're talking a model with only 27 million parameters. For context, many LLMs have billions or even trillions. And get this, it was trained on just 1,000 input-output examples for each task. That's tiny. And crucially, no pre-training on vast text data sets, and no need for those handcrafted chain-of-thought examples during training.
Wow, 27 million parameters, 1,000 examples. That's a completely different scale. So how did this small model actually do on tough reasoning benchmarks?
The results are, frankly, stunning. Let's take Sudoku Extreme 9x9. These are puzzles rated exceptionally difficult, even for humans, needing lots of backtracking. HRM achieved almost perfect performance, 74.5% accuracy. And the state-of-the-art CoT models they tested against?
Let me guess.
0%. Complete failure.
Okay, that's a stark difference. What about other tasks?
Similar story on maze hard, 30x30. Finding the optimal path in really large, complex mazes. HRM got near-perfect accuracy again, 55.0%. The CoT methods, also 0%, complete fail.
So tasks requiring planning, backtracking, looking ahead, HRM excels where CoT falls flat.
Exactly. And then there's the Abstraction and Reasoning Corpus, ARC-AGI. This is considered a key benchmark for more general AI reasoning involving visual patterns and abstract rules. HRM hit 40.3% accuracy on one version, ARC-AGI 1. That significantly outperformed leading code models like O3 Mini High, 34.5%, and even large models like Claude 3.78K, which got 21.2%. And remember, HRM is tiny compared to those models and used way less context.
They also did a direct comparison, right? A standard transformer model, same size as HRM.
Yes. A direct prediction transformer, 27 million parameters, trained the same way on the same small data sets. On Sudoku and maze, it failed completely, just like the CoT models. This really drives home the point. It's not just about model size, it's about the architecture. HRM's hierarchical, recurrent structure is fundamentally better suited for these kinds of reasoning problems.
Beyond the accuracy numbers, did they get any insight into how HRM solves these problems? Like, what's going on inside?
They did, and it's fascinating. They visualized the model's internal states during problem solving, and it looks like HRM actually learns to use different strategies depending on the task. It's not just one fixed algorithm.
Different strategies, like what?
Okay, so for the maze task, the visualizations suggest HRM starts by kind of exploring multiple possible paths at once. Then it prunes the bad ones, sketches out a rough path, and refines it. It looks a bit like a smart search. For Sudoku, though, the pattern looks more like a depth-first search. It tries filling in numbers, goes down a path, and if it hits a contradiction, it backtracks and tries something else, very much like how a human might tackle it.
Interesting. And for the ARC-AGI puzzles, those abstract visual ones?
There, the strategy seemed different again, more like hill-climbing optimization. HRM makes small, incremental changes to the puzzle grid, step by step, gradually improving it until it finds the solution pattern. So the big takeaway isn't just that it's accurate, but that it seems to be learning flexible, task-appropriate reasoning strategies. That's a sign of deeper understanding, maybe.
That flexibility is key. And the paper connects this back to neuroscience again, doesn't it? Something about the dimensionality of neural representations.
Yes, exactly. There's this principle in neuroscience that a brain area's ability to handle diverse tasks, its functional repertoire, is linked to the dimensionality of its neural activity patterns. Basically, higher-order brain areas, the ones doing more complex stuff, tend to operate in higher dimensional neural spaces. This gives them more flexibility, more capacity to represent different things distinctly.
And they have a way to measure this dimensionality.
They use a measure called the participation ratio, or PR. Think of it as the effective number of dimensions a neural representation is using. A higher PR means the activity is spread out across many dimensions, indicating a richer, more flexible representation, rather than being squashed into just a few dimensions.
Okay, so how does HRM measure up on this? Does its internal structure show this kind of dimensionality difference?
Remarkably, yes. This is one of the most striking findings, I think. After they trained HRM on Sudoku, they measured the PR of the low-level module state, ZL, and the high-level module state, ZH. The low-level module operated in a relatively smaller subspace PR around 30. The high-level module operated in a significantly larger subspace PR around 90.
Wow, a threefold difference. So the high-level planner uses a much richer representational space.
Exactly. And what's more, they found that the dimensionality of the H module, the high-level one, actually scaled with the diversity of tasks it was trained on. More diverse tasks led to higher PR in H. But the dimensionality of the L module, the low-level executor, stayed relatively stable regardless of task diversity.
So this hierarchy in dimensionality isn't something they explicitly built in, it just emerged.
Precisely. That's the crucial point. This dimensionality hierarchy is an emergent property of the training process. If you take an untrained HRM model, the PR values for H and L are low and almost identical. There's no separation. It means the model, through learning to solve these reasoning tasks, autonomously discovers this organizational principle separating representations into a high-dimensional abstract space and a lower-dimensional execution space. It's learning how to structure its internal thoughts, if you will.
That's profound. Is learning an organizational principle we see in biology? Is there a direct comparison there too?
There is a fascinating parallel. The ratio of the high PR to low PR in their trained HRM was about 2.98. Studies in the mouse cortex have found a similar ratio between higher order and lower order areas, around 2.25. It's intriguingly close, and this contrasts sharply with a problem called neural collapse, often seen in standard deep networks, where representations tend to collapse into a low-dimensional space, which can limit flexibility. HRM actively fosters this high-dimensional space in its higher module.
So it's not just avoiding a pitfall of other models. It's actively developing a structure that mirrors biological intelligence and seems crucial for flexible reasoning.
You've got it. It suggests HRM isn't just a bag of clever tricks. It might be tapping into some fundamental principles of how robust, flexible intelligence is organized, whether biological or artificial.
Okay, let's try to wrap this up. To recap, HRM is this novel, brain-inspired AI. It uses a hierarchical structure, two modules working at different speeds, to achieve really deep computation without the usual problems of instability or massive memory costs during training.
Right. It employs clever techniques like hierarchical convergence, that O1 approximate gradient, deep supervision, and adaptive computation time. And the result is a compact model, just 27 million parameters, trained on only 1,000 examples per task that absolutely dominates complex reasoning benchmarks like Sudoku Extreme, Maze Hard, and even RRC AGI. Tasks where current state-of-the-art LLMs using chain of thought often fail completely.
So this work really throws down a gauntlet, challenging the current dominance of purely transformer-based, non-hierarchical approaches. It presents a concrete, effective alternative to chain of thought for complex reasoning.
It does, and it moves AI closer to this idea of Turing-complete universal computation. That means having the potential to simulate any algorithm, to perform true step-by-step algorithmic problem-solving, not just sophisticated pattern matching. It seems to overcome some fundamental computational limits inherent in the standard transformer architecture.
Which leaves us with a really provocative final thought, doesn't it? If mimicking the brain's internal architecture, this idea of two brains working hierarchically at different speeds, developing different dimensional representations, if that's a key to unlocking true AI reasoning, what other principles from biology might hold the keys to the next big breakthroughs in AI? What does this tell us about the nature of intelligence itself, whether it's in our heads or in silicon?